talking, really this is a lot of stuff that we've already been doing. We're going to continue doing our integrals. It's just phrasing things in different ways and giving us additional practice with a lot of stuff that we've already been doing. We know that we've used the notation before that a capital F represents the antiderivative, which is the same thing as an integral. We know that if you have the capital F, you can do the derivative and you should get your lowercase f in there. So that's notation we've seen before. We've kind of touched on, but haven't really stated this a lot. You really have to watch the difference between a definite and an indefinite integral. Indefinite integrals were the ones where we had to put plus c at the end. And what we got was like an expression, 3x plus 2 plus c. You know, we had a formula for finding our antiderivative. Versus a definite integral, when you evaluate that, you get a number answer. So there is a difference there. If it's definite, you're plugging in, you're getting a number. It's the actual area under the curve. Versus if it's indefinite, you're getting a formula for finding the area under a curve. So let's just keep practicing our antiderivatives here. I want the integral of 10x to the fourth plus 2 secant squared x dx. So we can go term by term. 10x to the fourth.
2x to the fifth.
You have your x to the fifth, which would throw a 1/5 out in front. 10 times the fifth is 2. Are you guys okay if I start skipping that step where I write that part out? Minus 2 secant squared x. What has a derivative of secant squared? What do we need on this one? Plus c. Let's try one a little more complicated than we've done before. Okay, I have told you if it is a product or quotient, you can't just do the antiderivative of each piece. Because we know if we have a quotient, when we do the derivative, we have to do the full quotient rule. So it doesn't work that nice. Is there any way I could rewrite this problem?
Cosine times sine to the -2.
You could bring up a sine to the -2, but that just changes your quotient to a product.
Either that or change it to like cotangent secant or cosecant.
Sine squared is like the same as sine over sine. So you could rewrite this as cosine over sine times a 1 over sine. Okay, well that's just saying cotangent theta cosecant theta. Now initially that's not real promising because I still have a product. Is there anything whose derivative is cosecant cotangent?
Well, cosecant is a negative cotangent cosecant.
Derivative of cosecant is negative cosecant cotangent. So since this is a positive, when I do the antiderivative, it will be negative cosecant theta. And what do we need? Plus c. So we may have to manipulate our original problem a little bit before we can evaluate this. Alright, why don't you guys do 3 and 5. Do examples 3 and 5. I'm going to do 4 with you in a second. Let's try these. So example 3, what was your antiderivative? From 0 to 3. And so we get negative 27 over 4. Okay, next one, I had you skip to example 5 for a second. So what did you have to do first on this?
Change it. I changed
split up, reduce your t's there, so it's no longer a quotient. So then add 1 to your power, so the antiderivative of 2 would be a 2t. T to the 1/2, if you add 1 to your power, you get 3/2, so it gets a 2/3 in front. T to the negative 2, if you add 1 to your power, you get a -1, so you just need a negative in front. Evaluating from 1 to 9, so if you put in a 9, (32 and 4 times?
292 over 9.
Yeah, 292 over 9. So were you okay with those two? Example 4. Last time on your homework I took off problem 39 because it had a 1 over x squared plus 1 in it. And I wasn't sure you would remember how to do that. Remember way back when we were doing derivatives and there were formulas for the derivatives of the inverse trig functions. It was just a table in the book and I said I'm not going to make you memorize it, but if you ever needed it you could look in the table. That's where this comes from. So if you want, you can open your book up to page 214. That was the page with our table. So when we have 2x cubed, antiderivative would be x to the 4th. You'd have a 1/4 out in front times 2 would give me a 1/2. 6x, so x squared, so you need a 1/2 in front times our 6 is a 3. Then this thing, we have 3, think of this as 3 times 1 over x squared plus 1. We do not know the derivative or the antiderivative of 1 over x squared plus 1. But if you look at that chart on page 214,
tangent inverse.
that is the tangent inverse. So this is 3 tangent inverse of x. Just like I did with these derivatives, I'm not going to put that on the test or anything. But if I snuck one in on the homework, you could go reference the table to look it up. Okay, so then if we evaluate this, tangent inverse of 0 is 0. You could evaluate this a little more, but I'm not going to. I'm just going to leave this tangent inverse 2. Tangent inverse of 0, I knew that was 0 because it's like saying when is tangent equal to 0? Unless it's 0 degrees or 0 radians. If you were going to plug that in your calculator and evaluate it, you would need to make sure your calculator is in radian mode because all of our trig functions, our calc formulas only work with the radians. Alright, is this stuff okay? Really just more practice with our antiderivatives. Last thing we're going to talk about are some applications that go along with it. When we do antiderivatives, we have talked about it being the area under the curve. You might also hear that referred to as net change in area, the total amount of change in our area over time. So this shows up a lot of different places. The next few slides I just put examples of situations when you might see this. If V is the volume of water in a reservoir at time t, then the derivative would be the rate that the water is flowing in. So V is the total amount, the derivative then is the rate of change. So if I asked you to integrate that rate of change over a specific time frame, that would give you the change in the amount of water in the reservoir over that time period. If C is our concentration of the product of a chemical reaction at time t, the rate of the reaction would be your derivative. So if I asked you to integrate that rate of reaction and I gave you a definite interval, then what you're finding is the change in concentration between those two times. A few more, if I have the mass of a rod measured from the left to a point on it, that gives me my linear density as the derivative. So if I asked you to do the antiderivative of your linear density, that gives you the mass in between that segment. If you have a population growth, then if you integrate a population growth, a rate of change of population, you get the actual amount your population has changed during that time. We've talked about cost and marginal cost a lot. If I ask you to integrate a marginal cost, you're going to get your cost function. So if I give you definite intervals, that's the amount the cost has changed over that unit of time. We've talked about position and velocity a lot. Derivative of position is velocity. So if I ask you to integrate velocity, that will give you your change in position over a time period. There is also a difference between displacement and distance traveled. Displacement takes into account that above the axis is positive and below the axis is negative, and that's just your overall integral. If you just integrate from start to end, it takes into account and it will automatically give you the correct for above the axis being positive and below being negative. However, sometimes I may ask you for the total area or the total distance traveled, in which case you don't want to subtract anything off. If you get in your car and you go to Hannibal and then you come back and then you go back to Hannibal, those would be positives and this would be a negative. But if I asked you how far you drove, you wouldn't get to subtract off the distance between Hannibal and Monroe when you came back. You would have to do the absolute value there. So you just have to watch in the problem the context of how we want to evaluate that. So let's practice. A particle moves along a line so that the velocity at time t is given by this equation, measured in meters per second. Part A, I want the displacement during the time period, and B, I want the distance traveled. Okay. Displacement is just asking for your change in position from beginning to end. So displacement is just your normal antiderivative from where to where? 1 to 4. So if I do my antiderivative, we would get 1/3 t cubed minus 1/2 t squared minus 6t between 1 and 4. What does that give me? -9/2? Sure. That's my answer. How would you get a negative? What does a negative displacement mean?
You were more negatively.
Right. You spent more time going backwards than forward, or your overall change, you were behind where you started. traveled is going to be a little bit different. Because in distance traveled, I don't want any negatives. So we have to essentially make sure that we do kind of like the absolute value of this. Probably be helpful to figure out when this thing equals 0 so that we know how to break up our integral. So if I want, I could factor that. Multiply -6, add -1 would be a -3, and a +2. So that means I have to integrate. We're starting at 1. I'll need to stop at 2. Then we'll have to go between 2 and 3. And then from 3 to 4.
Is it, how come you stopped at 2?
Because it equals 0 there. That should be -2 though, shouldn't it? So I don't really need to do that. Let's try that again. So it equals 0 at -2 and 3, but since -2 isn't in my interval, I don't have to worry about that. So I'm going to go from 1 to 3, and from 3 to 4. That makes more sense, doesn't it? Okay, from 1 to 3. If you're not sure, you could look at a graph, you could pick a number. If I plugged a 2 in this, do I get a positive or negative number out? Do I?
No,
It's a negative. So what do I do to make it positive?
we're not negative.
Mm-hmm. If I put in a number between 3 and 4, it is positive, so we don't change our function. You could also look at the graph of this and just see where it's above and below the axis. Okay, so now we know our antiderivative. This would be -1/3 t cubed plus 1/2 t squared plus 6t from 1 to 3. And this one would be 1/3 t cubed minus 1/2 t squared minus 6t. 3 to 4, bless you. And, you know, we are approximating distance, so if you wanted to give a decimal, that is about 10.17, we said we were in meters. So that is the total distance that has been traveled in this scenario. That's counting forward and backward, both as positive measurements. Alright, is that okay? I think I'm going to skip the last one. It's estimating area under a graph, so it's gonna take us a little bit to get through, and it's really just something we've done before, you know, adding up, approximating what the area looks like, and working from there. So, I am done. This is the assignment. Game plan, what I have decided to do is tomorrow, we're playing catch up a little bit, and I'm trying to gain back today. We are going to do a take-home quiz over section 5.3 and 5.4. So 5.3 is what we just turned in, 5.4 is this. So tomorrow will be a work day. You can work on this assignment, you can work on the take-home quiz. Just remember my rules for take-home quiz. I don't mind if you look in your book or your notes, but please don't talk to one another, and I will compare your papers when I'm grading to make sure that you are doing your own work. So, if you're going to be gone tomorrow for track, you are welcome. I